It all started in 2001. It's when Udo Jüers invented the first modern quadcopter. And a couple of years later, he founded microdrones in Germany. So I founded my own company in the US in 2012 to develop payloads and software. What we wanted to do is really to master the whole workflow, starting from the mission preparation to the drone, the sensor to collect the data, and then the processing. In 2016, so we started with a drone, and we decided to focus on one application. It was surveying. In 2017, we released our first LiDAR payload, and in 2020, our first data processing software platform. So in parallel of that, you have GeoQ. It was founded in 2003 in Alabama by Lewis Graham and Jim Medlock. They were former employees of Intergraph, and they wanted to develop workflow for airborne application with point cloud and photogrammetry. They acquired Q-current software called LP360, which became the foundation and the core of our software in 2009. And in 2014, they decided to develop the drone applications. And in 2019, they released their first payload under the brand TrueView, combining LiDAR sensors and cameras. And at the end of last year, in 2021, so the group acquired GeoQ. So after the drone, we wanted to reinforce our payload and the software. So building on the strengths of the two operation companies, microdrones on one end, with the drone, the mission preparation software, and on GeoQ on the payload and the data processing software. And we decided to further invest and further develop our presence in the US, so having all the payload and software co-located in Huntsville, where we have all the development. Now we have all the pieces together, and we have the right technology and the right people to be the leader in LiDAR mapping in North America. And we go to market with two product lines. So LP360, which is the GIS software to process the data. It's a reference in the US. So it can be used to process your data coming from our own sensors, but also from third-party sensors. And we have TrueView, which are the high-end payload that we develop in-house, combining imagery and LiDAR sensor. So when we sell a TrueView sensor, we provide also a license of LP360. We can sell the package as a standalone, or we can also bundle it with third-party drone, depending on your applications. So our first market is the US. We have several governmental entities as a customer linked to GIS, like USDA, USGS. We have a couple of Department of Transportation of several states. And we have the big engineering firms, but also the smaller ones down to the land surveyors. Definitely the priority for us and the main focus is the US, but we have more and more requests coming from outside of the US. So we are planning to launch our product also in Europe this year. The whole workflow in-house, be able to master and adapt each step of the workflow to make sure that we have the right deliverable at the end, that's really the key of what we do.
So a few opening remarks. Be aware of vendor specs that focus on ideal scenarios. If you see a sensor precision spec'd out at 2 centimeters, but the range distance is at 20 meters, that's not a scenario that you're likely to encounter when you're collecting data. So the 2 centimeter spec, when flying at 20 meters, is not very useful to you when you're evaluating a sensor. And then sometimes those specs are maybe for a different industry. They're not for mapping, and so sometimes the specs that they give you may not be useful for mapping applications. Some of those, like a 300 kilohertz system with 2 returns being advertised as a 600 kilohertz sensor. That's not the correct way to represent the collection rate of a scanner. So some others you might see, the max range. So Obviously, everybody wants their LiDAR scanner to be able to collect data at an extremely long range, but they might say 270 meters at 80% reflectivity, and without knowing what normal reflectivity might be, you might think that's a really great number. So I've got a chart over here that kind of shows some various surface reflectivity values for different surfaces that you might encounter in the real world. So you've got sand, soil, wet soil, dry soil, forest, water, things of that nature. If you look at the top of the 80% mark, you notice there's just not a lot of surfaces up that high. So if you're advertising an 80% reflectance value, it's not a realistic number. It's not one that you're going to encounter in the real world. And then if you see range precision specs, make sure that that's accompanied by a range value, because precision and range are obviously correlated. The closer you are to a surface, the higher degree of precision you can get. The further away you are, the less precise it's going to be. So why use a drone at all? Time being the biggest one. So for traditional survey methods, if you're walking a project, it's a lot faster to fly your drone over the top of that project. So time is a huge increase in value when using a drone. Drones have become a lot more cost effective in recent years. So it's now it's cheaper than ever to purchase a drone and incorporate a drone into your surveying practices. Availability has increased and the price has gone down, and they're more and more available now. The entry price for getting into drone LiDAR is cheaper now than it has been. Your initial capital investment, you'll be able to turn that around and pay that sensor off a lot faster than most people think they can. It's worth talking about the differences if you're thinking about purchasing a drone LiDAR system, because drone photogrammetry operations are a lot cheaper because there are a lot more cameras available than there are LiDAR sensors. So they work well in most scenarios, but they struggle with certain types of complex structures like thin wires. If you're trying to model wires, photogrammetry doesn't do so well with those types of features. Vertical objects like buildings. Drone LiDAR systems are typically more expensive, but then the benefits of being able to get penetration through the canopy is huge. One, because you can model the surface beneath the canopy, but then two, it lets you take advantage of automatic ground classification algorithms like we have in our software, which I'm going to talk about later. So the best case scenario then would be to collect both. Like I can do drone LiDAR and I can do photos for photogrammetry all in one single flight. So in the simplest of terms, a LiDAR sensor is really two main components. It's a time of flight sensor, which measures the speed of light, right? I can send out a pulse of light to an object. I know how long it takes that light to travel to the object and back. And then the second component is the kinematic mapping component, which is the position and orientation. So it's not surprising that those two sensors are the two most important ones on a LiDAR scanner, and those are going to be the ones that determine how good your data, your final data is the LiDAR scanner itself and the position and orientation system. We call our systems a 3DIS or 3D imaging system. And so what is that? That's a fully integrated LiDAR and camera mapping system. So our LiDAR scanner and our cameras are all mounted to the same frame and are calibrated together, so we know exactly where the photos are. We know their position and their orientation in relation to the LiDAR data. So that allows us to colorize the point cloud a little differently than some of the traditional methods. So in the real world, you have colors all along the 3D spectrum, and so, but you know, in the traditional method, you can't see those colors. But with the 3DIS system, we can see colors on the sides of objects. So we have two cameras, one looking 25 degrees to the left, one looking 25 degrees to the right, and it has a slightly oblique view of the objects that we're modeling, and that lets us colorize the sides of objects. One on the left is showing the traditionally colorized point cloud. And so then on the right, I have a point cloud that was colorized. This is our TrueView 515 colorization process. So here I have a diagram on the left showing the LiDAR field of view in red and the camera field of view in black. So this is on the left is a typical LiDAR with a single camera integration. And you can see, so our systems are designed with a 120 degree field of view. They record LiDAR at 120 degree field of view. On the right, a TrueView 3DIS. So you can see the two black triangles there showing both cameras that are off nadir. So I've got the camera looking to the left, a camera looking to the right, and there's even a little bit in the middle there where they overlap each other. So we're matching a 120-degree field of view of the LiDAR with the two off-nadir cameras. And what this lets me do is then plan my mission based on the efficiency of the LiDAR data. And then I spread my flight lines out, and then I can cover more area in the same amount of time, or I can cover the same area in less time. For mapping, we typically talk about accuracy in terms of network accuracy or absolute accuracy, or you'll hear it called sometimes. And almost always those are referenced relative to checkpoints or control points. For precision, talking about is the thickness of the point cloud. If you looked at the point cloud from a side view, maybe along a hard surface, how thick is that point cloud? That's oftentimes what people refer to as the precision, although the metric for discussing precision is not the overall width of the point cloud, but rather the 1 sigma value. We want a system that is both accurate and precise. So we've got some examples of what a system would look like if it were accurate but not precise, or precise but not accurate, or neither or both. And ideally, we want one that's both accurate and precise. So we have a tool in our software in LP360 to measure the precision of a point cloud. This is almost always done on a hard surface because if you're in the grass, you're measuring the thickness of the grass along with the thickness of your precision of your sensor, so those are not very good places for that type of measurement. But on hard surfaces, we have a tool. I can draw a polygon within my point cloud, and it'll tell me how the precision level of my sensor. It'll tell me the 1 sigma, 1 standard deviation measurement of the point cloud. So the tighter that is, the lower the precision, the better the sensor. Be sure any accuracy assessments that are being presented to you are being done based on established mapping standards. In the US, we use the ASPRS. So they have well-defined vertical accuracy standards. And the typical way of measuring accuracy is relative to checkpoints, so surveyed targets on the ground. You have, I think the requirement is 30. So then you would compare those to your point cloud elevation and give you an indication of how accurate your point cloud is. That's the standard way, although there are other methods. And for horizontal, it's measured much the same way that vertical is, but typically you have to have some kind of identifiable target in the point cloud so that you can pick out the horizontal location. I've seen people use highly reflective tape, and they can use the intensity values of the LiDAR to do horizontal accuracy assessment, or you can use a vertical object like a curb or a building or something like that. As long as you know the XY location and you have a point, a survey marker, and then something in the point cloud that I can use to compare to that. When we're talking about precision of your sensor, that's typically measured within 1 standard deviation. So if I were to take if I take a profile of my point cloud and I create a plane along the mean of those points, and I would measure how far from the mean that those points are, that would be the measure of precision, but we do that at 1 standard deviation. So 68% of the points lie within how far of the mean, and that would give you a good indication of how precise your sensor is. So range specs, most of the time these are presented as slant range because the range of a LiDAR sensor typically doesn't really care which direction it is. It's the overall range, so the slant range is going to be the longest when you're flying your drone and you have your sensor pointed down at the ground. Your AGL flying height is not the max range, it's the slant range to the edge. And so beam divergence is how wide the beam of light is spreading as it's traveling further from the sensor, and this has an impact on the accuracy. So a very large beam is going to have a noisy return value, and so you're going to have a noisier point cloud. So high-end sensors have a lower beam divergence. So it determines the spot size on the ground. So at the sensor, it's a tiny beam, but by the time it gets to the ground, it's a fairly large spot on the ground, and so I've got some relative spot sizes of what some of the sensors produce. So for the LiVix scanner, the LiVix Avia scanner, this is what you would find in the L1. So at 100 meters, the spot size would be 48 centimeters by 5.2. The Pandar XT, this is what our TrueView 515 is built on. So 22 centimeters by 15 centimeters. And then obviously the Regal is 16 by 5. Looking at these, it's probably pretty obvious which one of these is the high-end sensor and which one is the low-end based on if I know a large beam on the ground creates more ambiguity and less likely to get an accurate return. So the bigger the beam, the less precise the sensor is going to be. So a multi-beam channel has multiple sensors emitting light at the same time, and most of these are built this way because they're automotive LiDAR sensors, and they've been repurposed for mapping. And so when you consider what their purpose is, they mount them on the top of the vehicle, and it scans looking out horizontally and down at the ground to try to capture objects. And so that's why they have multiple beams. So the picture on the right shows a 8-beam scanner in the middle, and then at the bottom you have the LP360. That's a 16-channel scanner. And then you have the single beam. So we have on top there, that's the Minivux, which is what our TrueView 655 and 660 is built on. That's a single channel scanner. So normally the more beams that it has, the more noisy the point cloud is going to be. You know, we talked about the LiDAR being important because you're going to have a more precise representation of the ground, but then where is that actually in space? So that your position orientation system is going to be what determines that. So the better your position orientation system, the better your LiDAR data is going to be. So all of our TrueView systems are integrated with the Aplanix IMUs, the APX15 and APX20. Those are, Aplanix has been making IMUs for a long time. If you're familiar with the manned LiDAR side of things, you've probably heard them before. So to summarize, when you're looking for a LiDAR sensor, the range, you should be considering the range. And you should be considering slant range in that, and that should be normalized to 20% reflectivity. Precision should be pretty easy for them to give you a precision value, and that'll help you determine if that's going to fit the needs for the projects that you're trying to do. If it has a high precision value, you're going to be limited to certain types of projects. Point density, you know, consider the types of area that you're mapping and what type of point density that you need. The field of view, you want at least 25 to 30% side lap on that for geometric correction. It's okay to go more side lap than that. In fact, there are cases that can be made that for heavily vegetated areas, having 50% side lap gives you, twice the number of points in the same area. So this is just kind of a general recommendation. Number of returns, we didn't talk about returns, but a return value is whenever it emits a beam of light and it strikes a tree branch, but then I get a return value from that, but then there's enough energy to continue past that tree branch, you get another return, and then I can continue to get returns beyond that until there's no more energy or it strikes the ground and I can't go beyond the ground. So the better the system, the more returns that it can get, but I would say you would need a system with at least 2 returns, else you're not really taking advantage of LiDAR data. Power supply needs to last at least as long as your flight, otherwise you're going to be, your system's going to be powering off mid-flight.
If you're not in the LiDAR business, or if you are in the LiDAR business, we still have something for you. If you need hardware, we got hardware for you. If you need software, our software is pretty good. If you need to make your data better, you need to strip a line, you need to create deliverables, all that stuff is in our software now. If you work in our ecosystem, if you will, you use some of our hardware products, you'll move into LP360, you see the stuff that it generates, this is just some of it. Accuracy reports, we all want to know our data is accurate, right? We have stuff in there where you can check a delta with your check shots. We have that in there. Classification tools, automatic and manual. Geocode the photos. If you've gone to thousands of data sets like I have, weird stuff happens. It's nice to stay in the same data set. I think when the software recognizes your hardware, that you have some advantages there because it knows a lot of things. Our software automatically pulls the most current calibration report. It's kept in another software we call Reckon on the GeoQ side. TrueView product family. Talk about the 435. It's the same Hesai Pandar sensor. As we move to the 515, it's just more pulses. You got 100,000 or 200,000 pulses coming out. When you get to the 655 and the 660s, the Regal sensors, Chad mentioned that, we used to have, we got cameras doing this, right, plus or minus 25 degrees off nadir. And now we've got a nadir camera, so you got 3 RGB cameras. On the 655 side, it's an APX15 IMU. The 660 side, it's the APX20. It's the Minivux 3, based on the Minivux 3, so that's what we got. 16 beams, 2 returns, or 32 beams, 2 returns. The Regal's 100-meter flying height. The other ones are 80-meter flying height. The 435 and the 515 have 2 cameras, and the Regals have 3. That's a brand new sensor. We did re-engineer that Regal sensor, though. It's a heavy. Y'all know the Regal's heavy. It's just big and giant heavy, right? We can fly that on the M300 now. We can fly on a smaller drone. So we do a lot of testing, lots and lots of testing at GOQ. We flew the systems. Of course, the 435-15 is exactly the same, except 100,000, 200,000 pulses. APX-15, 3.2 centimeter accuracy, pretty good. Of course, the Regals, again, the standard of the industry, 660. This is on 20 hard surface targets. It was actually flown. A lot of other stuff going on in the data set, but the hard surface target's 1.6 centimeters. If you get one of our systems, you get a little kit. This is what comes in there. All the system stuff. 1 battery. It says 2 up there, but there's really 1 because you get the external battery connector. So that way, on the 435 and the 515, you can run an external battery for the system if you want to. You can rent this, use the system. We'll train you on it. You get the software and everything else. So if you're relying on somebody else to provide you with information, data information that you need to complete the job, to generate your maps, so you can build somebody and make money, you might really want to consider this. It will allow you to be able to get into new markets, if you will. Another way to get in it, if you wanted to buy a system and own a system, is our low-end system where you can get 40 kinematic processing minutes. And this is APX-15. As you can see with the software, you get the full suite of software every time. With every one of the systems I'm going to talk to you about, I'll mention it probably 2 or 3 times, but you're going to get the whole thing. It's got strip align. It's also got the, you can create your own orthos in here. It automatically does the photos as well. You also get 5 Explorer licenses. So if you got customers, they want to look at the data and just, they can't do any manipulation, but they can look at it and stuff. So we move up from there to the 435 system. It's traditional, just a normal system. This is what you'd be moving up to if you want to move out of the 40-minute kinematic thing. It's the same sensor, everything else is the same. And you can upgrade to the 515 system. Again, we always provide a path to that if y'all want to do that. This is the 515. You can start off with that if you want to. Same software, everything else is the same, APX-15. If you want to move up to the Regal systems, it's a little different. It's got the triple cam on there, so you got left to right. Cameras is 20 megapixel per camera. We can go in a lot of systems. Free Flight, Harris, Skyfront. We've got mounts for all these. We've worked with all these companies in America, so you can do that if you want to. You want to set a base station on a known point. If it's not known, we can fix that problem. Okay, we can pull an Opus in our software. We have grab the Opus, it drops all the stuff in where it needs to. But if you set your base station out on a known point, it needs to be logging 1 second static information. That information will be pulled into the software to make the corrections, to make your data. Data sets, geoids, state planes, all that stuff. I wish we were all on metric system. I don't know if y'all do, but I wish we were. It would make my life much easier. We do some guest sensor stuff. So I talked to you about the L1. That data is difficult. I'll just say that. It's we've done some testing and stuff with it, but you can pull. We have a module inside of LP360, and then we do some noise reduction, and we make the data, do some things to massage the data to make it more accurate. We can do some other stuff with the DJI photogrammetry side as well. So if y'all have got some of those sensors and want to work inside of LP360, you can. And remember, you can bring any LAS cloud you want to inside of our software and do things.
So the things that you should look for, one, are ease of use. Obviously, if you're trying to learn a new software and you're trying to start generating revenue from your investment, the faster that you can learn the software, the sooner you can start capitalizing on your investment. So ease of use is important. It's also important because if you're trying to onboard new employees and get them up to speed on the data processing, it helps if it's easier to learn. Integrated position and orientation tools. You're collecting LiDAR data and your position and orientation. You need to be able to correct that. You need to be able to correct your position, correct the orientation so you can get an accurate point cloud. So our software allows you to geocode the LiDAR, take the raw data, turn it into a point cloud. It gives you options for creating the swath width. You can have range clipping, so I can stop it from geocoding points beyond a certain range. So anyway, the geocoding option, being able to turn your raw data into a point cloud. How well do those flight lines match in the areas where the surface is really the same? it's not uncommon to see, a centimeter or so of offset between those two. And so the strip-align tool allows you to force match those together. It corrects for dynamic errors in your orientation. 3D colorization. If you wanted to use colorization in your point cloud, it helps to be able to colorize in the same software so that you don't have to go to an external product to colorize your point cloud. Direct orthophoto generation. This is probably my favorite one, just simply for the fact that there's a lot of options for building an orthomosaic, and so our software has that integrated for you, and it's basically click 3 buttons and you can build an orthomosaic. Spatial reference systems, extensive support for spatial reference systems and transformations. It's unlikely that you're going to be working in the same coordinate system all the time. You're going to have a wide range of coordinate systems that you're using, so you want to make sure that your software supports the coordinate system that you'll be working in the most. Data visualization, that's a must-have. You have to be able to look at your data, analyze your data, and see if it's represents the surface that you expect. Point cloud classification, this is where we're starting to separate, I think, LP360 from a lot of point cloud software, is being able to classify surface modeling with break lines. I know everyone has used break lines at least at some point, and if they're building a surface model, we support polygons, polylines, and 3D points for a break line surface manipulation. So I think the vast majority of our customers that I've seen, their end goal is to build a contour file. That seems to be the most common, not to say that that's what everybody's doing, but I think that's the vast majority of our customers are shooting for 1-foot contours. That's what their goal is. Can it generate a digital elevation model or digital terrain model? And then are there value-added tools like power line extractions, volumetrics? So making sure that you have all of those tools in one software will save you a lot of moving around from software to software and lets you do all of your work within one program, and it saves a lot of headache. So normally, I've got the plan, the mission, and the flying portion listed up here, but after that's where the software comes into play. So we transfer our raw data, our TrueView systems transfers all of your raw data onto a thumb drive, and you pull that out of the system, plug that into your laptop. So that's where the software begins, importing the data into your project, running POSPAC to calculate your trajectory corrections and orientation corrections, geocoding LiDAR, doing accuracy assessment, debias, colorizing your point cloud, classifying, orthophoto, and then deliverables. So your accuracy assessment, this is probably the most important tool because you have to be able to prove that your surface is as accurate as it needs to be to produce the files that you're trying to produce from it. So if you have trying to build 1-foot contours, there's a very well-defined accuracy metric for that, and you need to be able to quantify your point cloud accuracy and confirm that, yes, my surface is accurate enough to produce 1-foot contours. And so being able to automatically classify the ground points, separate the non-ground from the ground, and then build a surface from that, that's the real advantage of ground classification. And so we have that tool within LP360. We also have manual classification. I'll probably show those off a little bit when I get to the manual classification part. Grid to ground, this one pops up from time to time where surveyors are working in a coordinate system that has a vertical adjustment to it, so then they've kind of deviated from the vertical datum, and now they're into a local transformation. So if you need to do that, we have a tool that allows you to do rotation, scale, and translation of your point cloud. Surface modeling with break lines, I think I glossed over this in our initial slide, but being able to manipulate your point cloud with a break line, eventually going to be something that you have to do if you work with enough point clouds. There's going to come a time when you have a void in the point cloud and you need to supplement that void with a break line. A lot of times stream beds are covered with trees, and so that's a good opportunity for voids in the points, and so sometimes your stream bed will have a void there where it needs points in critical locations, but if I can use the break line to digitize the center of the stream and then force the surface in that area to the stream bed, I can produce a surface that is much more accurate and doesn't have what looks like chunks of earth in the middle of my stream bed. Create a raw point cloud, check the accuracy, classify the ground, and then generate a shapefile, a contour shapefile or DXF shapefile, all in one software. We have some advanced workflows, like we have a tool that's able to identify planar surfaces and then classify the building rooftop into the building class. We have a couple of customers who are construction-based companies that are flying their stockpile inventory regularly and calculating their volumetrics within LP360. You can classify the tops of the rail and then create a vector layer along the center line of the rail. Transformations, classified by features, and then model key points. I don't know if you've heard of model key points, but a model key point basically selects points at strategic areas of the point cloud so that you can thin the point cloud but not reduce the integrity of the point cloud. So we were involved in this transmission line project in Brazil. So it was a company that flew these transmission lines, and then we processed the data. So this company flew 220 kilometers of power line in Brazil with our 515. And it was all processed through LP360 Drone. We ended up classifying 746 towers, and then we were able to update their database with the correct tower height. So during this project, we found 922 danger encroachments. So they had some metrics that they were using to define a massive value increase, because the benefit here is you're able to more efficiently allocate your resources. You're trying to send a crew out to trim these vegetation encroachments. It's better to send it where they're needed the most, and so that's why this is a really valuable workflow. So we're running the POSPAC processing engine. We provided an interface within Evo so that basically we take all the information that you would need to create a good trajectory solution and kind of limit some of the other options. Makes it a much faster workflow. When we built our TrueView system, we built an interface for Metashape. So LP360 Photo is running Agisoft's Metashape processing engine. And so since we know the position and orientation, when you buy the sensor from us, we calibrate the cameras. So we know the camera calibration. We write all that information to the image header. The only thing that the user has to do is open the dialog, check the box on all the layers that you want to use to build your orthomosaic, and then click Submit Job, and it builds an orthomosaic and brings it into your software. So it's super easy. And then of course Strip-Align is integrated within LP360 as well. So in the screenshot here, I've got a couple of layers. I might have, if I did 3 flights to complete a project, I would have 3 LAS layers. I would just check the box next to each of those, and then it would strip-align all of them together into a single LAS layer. Our LP360 Explorer, this is a tool that, so if you buy a sensor from us, you get the software license. You also get 5 Explorer licenses, and this is more like an advanced viewer, I guess. So it lets you bring in data into the project, and you can view your point cloud data. The license level for the Explorer license doesn't allow you to do any processing, but it wasn't designed for that. It's more for other people within your organization that want to view the data but don't necessarily want to process it, right? You're going to process it, send them a finished product, and they want to look at it and view it. That's what the Explorer is for. And you can see here this example where we clicked on one of the point cloud, and you can see that that's an insulator, it looks like. So in addition to all the LiDAR tools that we talked about, we also offer photogrammetry tools. So if you have a Phantom 4 RTK or a P1, you can PPK process your photos in there. Take the raw data from the P1 or the Phantom 4 RTK, bring that straight through Evo, retag your photos with a more precise position, and then we write the position to the image tag, and then you can either process through LP360 Photo, or if you want, you can take it to Pix4D or whatever other photogrammetry software you'd like to use to build your ortho. When you buy a sensor, so we offer 2 days of training every month at our office in Huntsville. There's a pre-scheduled, you can go online and register for those. And if anyone wants to just come by and watch us process a data set, collect a data set and process it, it's 2 days a month, back to back. So we do the first day, we cover flight prep, installing the hardware, sensor operation, and we go out and collect a data set in front of the class, and then we process that to a colorized point cloud. And then day 2 is where we will have everybody import the data onto their laptop and process through the data themselves. So this is for the in-person training, so this is free to you if you purchase the system, but it's on predefined dates, and so you just have to pay for your own travel to attend those. If you did not want to travel, we do offer an online training. And so that's also pre-scheduled dates, 2 days a month. And typically we haven't even put a limit on the number of times. So we've got customers that come back month to month, repeated training. So our support, we've always taken pride in our support. That's why we've tried to put people in support that have experience with the products, because we want our customers to be happy after they bought the sensor. We have a web page where we have articles that we've written. We've got case studies. We've got some of our video tutorials. So feel free to go check those out. Hardware troubleshooting, sensor calibration. We do offer calibration services. So we're going to calibrate your system, your sensor. When you purchase it from us, you have a good feel for your sensor's accuracy. You start to see that degrading, then you might want to reach out to support and let them know. From there, we would come up with a plan for you to fly a mission and send us your data for calibration. All right, so I'm going to do a software demonstration. I'm going to take a TrueView 515 data set. I'm going to process through bringing in the raw data to a colorized point cloud, strip-aligned point cloud, and then I'll show you one after we smooth it, and then we'll QC it, show you the QC tool, and then I'll show you the final point cloud, ground classified point cloud. So I've opened the software. I've got a dialog that pops up that just asks me a few options, what I want to do to create a new project. If I had an existing LAS data set, I could do that and import the LAS directly, but we're going to import TrueView data. I choose if I'm importing flight to a new project or if I'm creating an archive. So we have the concept of archiving your data. You can take your raw flight data, your base observation, your coordinate, all the project information. We zip it up into an archive, and you can preserve your data that way so that if you need to come back and process raw data, you have all of the associated files with it as well. So it's nice for storing raw data for long-term storage, I guess. And then we have the guest archive there as well, the guest option as well. But I'm going to import flights into new project. On this dialog, I would either bring in a folder, the raw data folder. So if this came straight off of the LiDAR system, I would use the folder. Or if I'm importing an archive, which is what I'm going to do, is bring in an archive. So it just gives me some information about the sensor type, start and stop time of the cycle. I'll just move on to the next. It's already showing my base observation file. If I hadn't imported this, because this is archived, this is already saved into the archive for me. But normally on a raw data project, I would be importing that file here. Just choose your output root folder location. This is where it's going to create my LP360 project. I would give it a name. Okay, so I give it a name, and then I would choose my coordinate system, what I want my output data to be, what coordinate system I would want those in. We've got a pretty robust coordinate system library. Every time we update the software, we update the coordinate system library. So every time, you probably notice this, if there's any existing customers in the crowd, you'll know that every time you update the software, it tells you have to update your coordinate system library, and that's just to keep those up to date. Now I would input my base latitude, longitude, elevation, and then my ellipsoid height, and then say import. All right, so when I bring my raw data in, I can see the files associated with my flight. It also gives me this Google Earth background, and so it kind of gives me an idea to make sure that I'm in the right place and shows the correct coordinate system. So I'm going to bring this processing toolbar off to the side to highlight the buttons on it. So the processing workflow to get to a colorized point cloud is very simple. It's a 4-step process, and the buttons are in order of the steps that you need to complete them. So step 1 is POSPAC processing. Step 2 is creating flight lines. Step 3 is creating trajectories, and then step 4 is geocoding LiDAR. So I'm going to go through those down the line and complete step 1, 2, 3, and 4. So it's just that it's that simple. So this is where we're going to set up our POSPAC. This is the step that's going to do the PPK processing and the orientation correction, is running the POSPAC processing engine in the background to create our trajectory, or sometimes you'll hear it called an SBET, a smooth best estimate of trajectory. The first page is just some information about the sensor. If you're a subscription-based customer, it'll show you your point balance and the estimate of the amount of points it would take to process this for subscription-based customers. Here's where I would also choose If I wanted Smart Base, if I had TrueView points and wanted to use the Smart Base option, I could do that. And then PPRTX. Next page, we've already defined these on the import, so it's just an opportunity for you to modify these if you maybe input them incorrectly, double check them before you submit, but really nothing to do here. This page, this is going to change, but I'm choosing the output coordinate system of my trajectory. Eventually, we're going to do away with this. You don't need to even do this anymore. We can see the options we have. So I'm going to choose orthometric heights for my point cloud. I'm going to go with geoid 12B on this, or geoid 18. And then I'll make sure I choose the units, the output units that I want. And that's it. I'll click submit. Then it will post-process my trajectory, and then I'll end up with a smooth best estimate trajectory file that allows me to geocode my LiDAR. This will take a few minutes. I actually already have the file that I need for this, so we're not going to wait on this to process. But this basically, at this point, I'm waiting for it to tell me that this process is completed. So we're downloading the results now. All right, so that's done. It says it completed successfully. Do I want to look at the POSPAC report? So this is another useful tool, I think. It's if you've never looked at the POSPAC report, I'll scan through it really quick, but it's got a load of information in here. A lot of it's probably not necessary until you get into, if you had problems and needed to debug, a lot of this stuff is not useful until you're in that type of situation. But it has a lot of information that is very useful, things that I'll look at. I'll look at the percentage of fixed versus float solution. I'll look at the number of satellites in the solution, and then I'll go through and look at the estimated position accuracy. So my trajectory is estimating 2 centimeters. At the very end of the flight, it gets up to, it's still 2.22 centimeters, or 2.2 centimeters. So trajectory is very accurate. These are some things that I would check as I'm processing every project, if I see something crazy here, I would know immediately that I can't get good LiDAR data from a bad trajectory, so I would need to basically start debugging there. All right, so we completed step 1. Move to step 2. We're chopping up our flight lines. We're going to basically choose which areas of the flight I want to keep LiDAR data for. So our system records data once we exit a proximity mode. I hadn't spoke much about that, but the drone flies 30 meters from the takeoff location. The sensor begins recording data, and we record continuously until you come back into that proximity. All right, so I'm going to compute flight lines. It'll automatically chop up the flight lines based on some of these numbers, and then I can go in and you can see some things that it picked up, like these sensor calibration lines. We do a calibration maneuver at the beginning of the flight, so I'll just take those out. Okay, so I'll save that, and now I have created a file that represents the flight lines where I want to keep my LiDAR data. And so then I move to the third step, creating TrueView trajectories. This basically creates a trajectory file for each one of my flight lines. It also downloads the calibration from our Reckon webpage. So we store your sensor calibration online. We download the calibration from there, and we also, in this step, we are updating the EXIF tags of your photos. So a lot of things combined into this one step, but basically all you have to do here is click the button, and we tag your photos and calculate your TrueView trajectories. All right, so we've got some photos that are outside of our trajectory, which is common, so I'll just say yes. Yep, so now all the photos have been tagged with the correct position and orientation. So now I'm just going to geocode my LiDAR. Okay, so there's our colorized point cloud. I'm going to toggle this Google Hybrid layer off. All right, so now we have our colorized point cloud, and I'll just use the 3D viewer and we'll take a look at some different areas in the project. So fully colorized point cloud. Now we would move on to the second step. And so now I'm going to draw a profile down the center of the road and let you take a look at this, the point cloud thickness. So right now I'm looking at the point cloud. I'm going to display by point source ID. Those are two distinct flight lines, and they're not separated by much. Those are around a centimeter of separation there. But we can improve that, so that's plenty good enough for doing contours, but if you can make it better, why not? So I'm going to run the strip-align tool, and I'll show you how to run it. We won't wait on it to complete, but so I open the dialog. I have the number of LAS layers that I want to strip align. So if this is a 3-flight project, I would have 3 LAS layers. Just check the use box next to each layer, and then give it a name. So LAS strip align. I click submit strip align job, and now that's it. That's all you got to do is strip align your data. As simple as that. So when it's done, it'll tell me in Job Manager here that I have my project is complete. Right now it's saying that it's in progress, but you can see I ran this one a couple days ago. It took 3 minutes to complete, so not that long, but I've already got a LAS data that's been strip aligned, so rather than wait, we'll just move on. So now I'm going to import a LAS data set from another project. So this is how I would import my raw LAS data, if anyone's curious. So I'm looking at the original LAS layer we created, and this is the profile window that I'm viewing here. So I'm seeing only the points within this square box here. And I'm just going to toggle over to the strip align LAS layer that I just brought in, and before we move along, I better rename that. So I keep them separated. So I'm going to toggle over to the LAS strip align, and notice the points at the bottom. Watch how those colors that are kind of visibly separated, watch how they're then squeezed together. So I'm just changing to the layer that has been strip aligned. So now they're intermingled together, and you can barely tell them apart from each other. So here, notice there was a column called use. I kind of glossed over the fixed column, but what I would do is check the box there and use the fixed layer as the reference layer, and then it'll fix the data to that. Now the caveat is this only works with our sensors, doesn't work with other LiDAR data or outside sensors. So you have to have a TrueView system. So that was the kind of the deal that we worked out with Strip-Align, is that you can only use it with TrueView systems and an L1, so we can use this tool on L1 data as well. But there are other things as well, like it can't just be like a random LAS data set. It has to be imported into the project. We have to have the trajectory, so it's using your trajectory to make these strip alignments. Okay, so the next step, normally what I would do is I would run a smoothing algorithm on. We have a smoothing tool that runs a robust least squared algorithm to try to thin the point cloud down. It's very easy to run. Again, there's no options for it. You just choose the point cloud task, and I tell it to run the task, and it'll smooth the point cloud for me. That one took, on this data set, it took 6 minutes or 7 minutes to smooth the point cloud, so I'm going to, rather than run it, I'm going to bring that in, save us 7 minutes. So now watch the thickness of the point cloud now as I've imported the smooth data. So this is the same data set, just with the smoothing algorithm ran on it. Same location. And now it takes that down to razor thin. If I wanted to, I could run the smoothing algorithm using a polygon and just smooth part of it. I would choose my task and then tell it to run by polygon and then choose the polygon that I had imported. Okay, so now we've created our raw point cloud, we did the strip line, and we did smoothing. So now I'm going to, normally at this point I would probably export a DEM so I can build my orthomosaic. That takes about an hour and a half on this data set. So we're obviously not gonna wait on that, but I'm gonna bring in the orthomosaic that I built from this data set. So this is our orthomosaic, and you can see these are fairly high, high quality orthomosaics. I just kind of zoom it in and let you see some of the different artifacts. And this is the LiDAR case here, so I can almost see the shape of the LiDAR sensor there. It's pretty good. All right, so I brought in the control point layer. These were shot in by the surveyor on site. They sent us a CSV file, and we imported that into Evo, and now we're going to go through and check the accuracy of this point cloud. So what it's going to do is it's going to display each point. It's going to display the control X, Y, and Z, and then I'm going to click in the point cloud, and it is going to give me the surface elevation plus the X and Y location that I click, and then it'll give me some statistics about that. So I'm just going to zoom into the map and then click on the point. It drives me to those points. That's really nice, so you don't have to go and find them and hunt them down. You just click on it and it drives you to the point. So I've got a red dot representing the shape layer, that's the control point layer, and then I can visually see the target in the orthomosaic. And so it's doing Z from the point cloud, and then we're doing the horizontal from the orthomosaic. So all I do is I'm going to pick out a point in the center of that target where I know the survey marker was shot. I'm going to click there, and then it's going to give me a delta value. And I click on the second point, and it takes me to the next point in the list, and I do the same there. Click on the center of the target, and I go to the third, and I just go through the entire project doing this. And the whole time it's generating these statistics for me. Okay, so horizontally, so this is, we talked about the QC report and some of the numbers that are beneficial to knowing your overall point cloud accuracy. So having the mean error is valuable, but it's not the only statistic that's important. You need to know the standard deviation of the mean. That'll tell you, are my points all over the place, or are they fairly tightly grouped together and my mean is just shifted off of where it should be. Error range, this tells us it's just the minimum maximum. So I've got the error min, the error max. This is just the distance between those two. In and of itself, not an extremely valuable statistic, but it does give you a good indication if your point cloud is tightly grouped together. If the error ranges are narrow, that's an indication of a good data set and a good sensor. Okay, so I've got a root mean square in the X of 0.03 feet, so let's say rounded up to 400ths. On the Y, we've got 500ths. Overall planimetric, 600ths. And then our vertical RMSE is 300ths. And we tell you the minimum contour interval you can support. This is based on ASPRS accuracy standards. So this data set can support 1/10 of a foot contours. It's pretty good. So at this step, I would make a determination, do I need to debias the point cloud or can I proceed with classification? So the mean error here is 0 and our root mean square is acceptable for 1 foot contours. So I would say we're good to proceed. And the point cloud that we're using now, the smooth one, it already has a ground classification on it, so I'm going to toggle the point cloud back on. So you can see this was done automatically, so this is done our automatic ground extraction tool. So initially when the point cloud came in, it was all created, never classified. We run the ground classification tool on there. It classifies our ground for us. I'll draw a profile across some of these trees and let you see what that looks like. So the orange points are ground classification, the gray points are the created never classified, and you can see did a nice job of extracting the ground from that. And so now the idea is that I can go in and create a surface from point classifications, and I can say only generate contours on the ground classification, and I can basically strip back the vegetation and have a bare surface. So that's what let's take a look at what the ground would look like without all the other points. And let's see if this were a continuous surface. And so there's this entire property with no trees, no vegetation. Just strip that back. The next step I would do is export a contour file based on this. And it's user-defined interval, so if 1 foot contours are not what you're after, you just change the interval. So I'm going to bring in a contour file that was generated here. This step only takes about 3 minutes on a project this size. And there you have it. It's a 3D contour file. I can draw a profile across the road and let you see that you can see it now, that those files, those lines exist in 3D space. And now you have a completed project. Or you could take this file. I think a lot of people would take this and migrate this into CAD and then build a survey plat from it, or whatever the final deliverables ended up being. I can export. So you can do shape, DGN, version 7 or 8, DXF, and then KML. You can do just your standard ASCII formats. That's a good one if you're using a software that maybe doesn't support some of the more traditional formats, but surely they can probably ingest an ASCII format, which is just a XYZ and a classification. Point shape file, microstation, DGN, and then your AutoCAD DXF.